Let's look at chi-square goodness of fit tests for the binomial distribution. We can use a chi-square test to test the null hypothesis that the data comes from a specific parametric distribution. For example, we might want to test whether the data comes from a binomial or Poisson distribution, or even a continuous distribution such as the normal distribution. Let's look at an example to start. Suppose a person claims that the great NBA Hall of Famer Larry Bird's free throw successes follow a binomial distribution with a probability of success of 0.8. What does the observed data tell us about this claim? Let's restrict ourselves to the 1980-81 and 81-82 seasons. In these two seasons, Larry Bird shot 338 pairs of free throws with the following results. On 5 occasions, he missed both free throws. On 251 occasions, he made both, and on 82 occasions, he made one and missed one. On all of these occasions, he was awarded a pair of free throws. In basketball terms, it was not a one-and-one situation. Let's go back to the claim. We're going to test the null hypothesis that Larry Bird's number of successes on 2 free throws follows a binomial distribution with a probability of success of 0.8. The alternative hypothesis is going to be that the null hypothesis is wrong, or that the distribution of the number of successes differs from this in some way. That could mean that the binomial distribution is reasonable, but this probability of success is not, or it could also mean that the binomial distribution is not reasonable. For example, the independence assumption might be violated. Now let's calculate the expected counts under the null hypothesis. Or in other words, let's calculate what we would expect to get on average if the null hypothesis were true. Here's our binomial formula, and we are working with an n of 2, and the hypothesized value of p from the null hypothesis is 0.8. And so we are going to use this binomial formula for these different number of makes. And if we were to do that, we would see that the expected proportion for 0 makes is 0.04, or in other words, around 4% of the time we would expect him to miss both free throws. 32% of the time we would expect him to make one and miss one, and 64% of the time we would expect him to make both. To get our expected counts, we simply multiply these probabilities that we worked out by the total number of pairs of free throws that he took. And we work out that we would expect to see 13.52 occasions on average where he missed both free throws, 216.32 where he made both, and 108.16 times that he made one and missed one. Here's a comparison of the expected counts we just calculated and what was actually observed. And we see here that on 251 occasions, Larry Bird actually made both free throws. Under the hypothesis of a binomial distribution and a p equal to 2.8, we would expect him to only make 216.32. So to my eye at least, that looks like quite a bit of a difference. Similarly over here, he missed both on only 5 occasions, but under the null hypothesis, we would have expected to see 13.52. So to my eye at least, there looks like there's a real difference there. But are those differences big enough that we can say there is a statistically significant difference? Are the observed counts different enough from those expected counts that we can reject the null hypothesis? We're going to use our usual chi-square test statistic. We're going to take what we observed and we're going to subtract what we would expect to get on average if the null hypothesis were true. We're going to square that difference, divide by the expected, and then add that up over all cells. Here are the calculations for a test statistic. For this first cell, we would take the observed count of 5, and we would subtract the expected count of 13.52, square the difference, and divide by 13.52. We would then do similar things for the other 2 cells. And if we went ahead and did all of these calculations, we would find that our chi-square test statistic is equal to 17.26. Now we need to find the p-value. Under the null hypothesis, the test statistic will have approximately a chi-square distribution, but we need the appropriate degrees of freedom. The degrees of freedom are the number of cells minus 1, or in other words, the number of terms that we're adding up minus 1. And so here the degrees of freedom would be 3 minus 1, or 2. So let's plot in a chi-square distribution with 2 degrees of freedom. Here's a chi-square distribution with 2 degrees of freedom. And the observed value of the test statistic is over here somewhere at 17.26. The larger the value of the test statistic, the greater the evidence against the null hypothesis. If the observed counts are very different from the expected counts, then the test statistic is going to get large and there will be evidence against the null hypothesis. And so the p-value is going to be the probability under the null hypothesis of getting this value or something even larger. Or in other words, the p-value is going to be the area to the right of the observed value of our test statistic, 17.26. And if we go to software, we can see that that p-value is a very small number. The p-value is approximately 0.0002. So we have a very small p-value, indicating very strong evidence against the null hypothesis. And here again is our null hypothesis, that Larry Bird's number of successes on 2 free throws follows a binomial distribution with a probability of success of 0.8. And we tested this null hypothesis, and we found a p-value that was approximately 0.0002. A very small p-value indicating very strong evidence against this null hypothesis. So we have very strong evidence that this is simply not true. Now this could mean different things. It could mean that the binomial distribution is not reasonable, or it could be such that the binomial distribution itself is reasonable, but this probability of success is not. And as we'll see in the next example, it looks like Larry Bird made free throws with a success rate a little bit higher than that. In practical problems, we often don't have the parameter values specified in the null hypothesis. We often use data to estimate it. So let's look at a slightly different null hypothesis. Let's test the null hypothesis that Larry Bird's number of successes on 2 free throws follows a binomial distribution, but without a specified value of p. To test this, we're going to use a very similar method to what we just did, except we're going to have to use the data to estimate p, and then there are a couple of subtle differences as well. We're going to estimate his true probability of success with the proportion of free throws that he made, and this is simply going to be the number of free throws made over the total number of free throws taken. And our p hat then is going to be equal to, well, on 5 occasions he made 0. So the numerator is going to start with 5 times 0. On 82 occasions he made 1, so I'm going to add 82 times 1. And on 251 occasions he made both, and so I'm going to add 251 times 2. In the denominator, it's going to be the total number of free throws taken. Well, if we add up the observed 5 plus 82 plus 251, we have to be a little careful because on each of these occasions he took 2 free throws. And so we need to multiply that by 2 to give us the total number of free throws taken. If we work this out to 3 decimal places, this is going to be 0.864. And that is our estimated probability of success. The calculations are going to proceed in a very similar fashion to what we've done already. We use the binomial formula with an n of 2, except we've got a different value of p that we're using. We're going to use this p hat value that we just calculated of 0.864. That's what we're going to use in our binomial formula. We're going to do this for all the possibilities of 0 successes, 1 success, and 2 successes. We're going to use the binomial formula with an n of 2, and 0.864 for p. If we were to do that, we'd get expected proportions of 0.0185, 0.2351, and 0.7463. I'm doing some rounding here to make it look reasonable on the slide, but you should carry many decimal places throughout the calculations. To get our expected counts, we simply multiply these expected proportions that we calculated using the binomial formula times the total number of pairs of free throws that Larry Bird took, which was 338, and we get these expected counts. Now let's compare those expected counts we just calculated to what was actually observed. On 251 occasions, Larry Bird made both free throws, and if our null hypothesis were true, we would expect to see on average 252.26 times. To my eye, those values are very close. Similarly, over here, at 0, we observed 5 times where Larry Bird missed both free throws, and we would have expected to see that 6.26 times on average. Again, fairly close. So to my eye, these observed counts are quite close to the expected counts, indicating little if any evidence against the null hypothesis. But we really should carry out the formal hypothesis test. To do this, once again we are going to look at each cell individually. We're going to take the observed count, 5 in this case, subtract the expected count, 6.26, square that, and divide by the expected. We are then going to do that for the other two cells as well. If we were to carry out this test statistic, we would see that the value of the test statistic is 0.34. We again need the p-value, which means that we need the appropriate degrees of freedom. And it might be tempting to say that we have 3 cells, and so the degrees of freedom are 3 minus 1, but that's not quite right here. An important point to note is that we lose an extra degree of freedom for each parameter that is estimated from the data. And in this case, we used the data to estimate the parameter p, and we lost 1 extra degree of freedom along the way. And so here the appropriate degrees of freedom are 3 minus 1 minus 1, or 1. Now let's plot in a chi-square distribution with 1 degree of freedom. Here I've plotted in a chi-square distribution with 1 degree of freedom, and the observed value of our test statistic is 0.34, which is somewhere around there. The larger the value of the test statistic, the greater the evidence against the null hypothesis, and the p-value is simply the area under the curve to the right of that test statistic, or in other words, the probability of getting this value or something even larger if the null hypothesis were actually true. And if we go to software, we can find out that the p-value is approximately 0.56. Now this is a large p-value, indicating no evidence against the null hypothesis. Here again is our null hypothesis, that in these years Larry Bird's number of successes on 2 free throws follows a binomial distribution. We tested this null hypothesis, and we found that the p-value was approximately 0.56, a large p-value, indicating no evidence against this null hypothesis. Or in other words, there is no evidence that in these years, Larry Bird's true distribution of the number of successful free throws differs from the binomial distribution. In simpler and slightly looser terms, the binomial distribution might provide a reasonable approximation to Larry Bird's true distribution of the number of successes in 2 free throws.